черное. Можно же было на черное, на самом деле.
Я сейчас О, что-то идет?
О, да, вроде теперь идет. Давно вас не видел. Очень приятно. So let's start. So first of all, please inscribe your name and email in the list. This list is for emailing home assignments to you. Зеленый горит, да.
Может, это на пульте?
А что должно быть на пульте? Okay. So, a few formalities. First of all, there will be no final exam. Everybody will be graded just for home assignments. And there will be 20 home assignments, 5 problems each. And then I will divide the total number of problems by 10 and get your grade in the end. Well, pardon me? No, 20 assignments, 5 problems each. It's 100 problems total. So I divide by 10 and get total final grade. You're welcome to submit them just in hard copy or send me whatever tech files, or but very readable anyway. Otherwise, I will not even try to grade it. And then another formality is we have to decide what to do in this class. So, for example, for today, I could not prepare any lecture at all because I didn't know what to talk about. What are you interested in? Say, do you know the basic symmetric functions like elementary, complete, monomial, power functions? So, well, there is a ring of symmetric functions, and it contains E, H, M, P, and S. So please raise your hand if you know what it means.
Я не знаю, кто такие М. Все остальные знают.
Okay, so please raise your hand if you know.
It is letters of the English alphabet.
No.
Вот all of them.
So I conclude that the majority does not know what it means, yeah? And then we'll have to start from scratch, so to say.
Okay, I know three. Yeah.
Three like this? No?
H.
And what else? P? These are sure functions.
Yeah.
Then. So okay, if I if I tell explicitly, maybe the result changes. So these are elementary, complete, monomial, power, sure. So let's take another vote. So who knows what it means? 1, 2, 3, 4, 5, 6, and still the majority does not know, I think. Then I'm sorry, we'll have to start with from scratch, just with basic definitions of all of these. Okay. Still, pardon me? I don't know.
У нас на курсе Альшанского они называются гомогенные, homogeneous.
Homogeneous. Yeah, maybe it's a better idea. For example, why these functions are called sure functions? They were introduced by Jacobi. Okay. Still, I will start from formal definitions next time. And today I will give some general overview and introduction. Well, maybe let me ask you, who knows the cohomology of topological spaces? Cohomology, like cohomology of X with coefficients in Z. So who knows this? Maybe majority knows this. Okay, so then I will probably will never need it in the course, but today I will mention it just for motivational purposes. If you don't understand something or anything at all today, it means nothing. It will have no relation whatsoever to what will follow. So today, just pure motivation. The first motivation comes from Israel Misevich Gelfand, who claimed that there are three sources of interesting problems in mathematics. So first is physics, certainly. Then second is geometry. And third is number theory. So these are essentially the only sources of interesting problems in mathematics. For example, in the high school, they usually learn analysis or algebra, but these are just technical tools. They don't usually provide interesting problems by themselves. There are notable exceptions, but as a rule, just these are the sources. Indeed, say, mathematics, it's a Greek word which means studying something. So mathematicians are just students in Greek. In Chinese, mathematics is something like shu xue, which means exactly studying of numbers. So it's like number theory. But certainly you've heard that the mathematics was well developed in China like 5,000 years ago. For example, what's called row reduction, yeah, in Russian Gauss method, is due to Chinese mathematicians. Certainly at that time, like 5,000 years ago, there was no real number theory. So what did they mean by studying numbers? They actually meant counting things. And counting things is combinatorics. So the actual root of number theory is combinatorics. The numbers themselves did not exist in the beginning. There are just abstractions needed. They are tools for counting things. In mathematics, it often happens that technical tools become the real substances to study. Maybe the most famous example is L functions that were introduced by Dirichlet, just say to prove this prime numbers in arithmetic progression theorem, but then they became the central object of study of modern mathematics in the last century. And the same thing happened to numbers. First they were introduced just to count objects, but then they became interesting objects to study by themselves. So in fact, this is an outgrowth of combinatorics. And combinatorics is, in a sense, the base of the whole mathematics. Let me give some examples of counting problems I mean. So certainly modern combinatorics contains very many things like combinatorics of graphs. And we will have nothing to do with this. And I myself know nothing about combinatorics of graphs. So we'll do some other counting problems. So the first example of a counting problem so-called Schubert calculus. And by the way, while we're interested in linguistics, calculus means just stones or small stones, pebbles in Latin. So it's again like counting things, counting small pebbles. So what it is about? Well, there are Grassmannians of k-dimensional spaces in n-dimensional spaces, well, over C, over complex numbers. And I hope everybody knows what it means. Yes, well, this is the moduli space of k-dimensional subspace in n-dimensional space. Like, for example, Grassmannian 1n is the projective space n-1, moduli space of lines in n-dimensional space. You don't, why are you?
Now I understand.
Pardon me?
Now I understand.
Yeah, great. And there are such things. And this very row reduction I mentioned implies that, well, the Pn minus 1 is the union of an minus 1, its final, finite affine part, and then, well, maybe I should say Pn minus 2. But then this can be decomposed similarly. So what we get is a n minus 2, and so on, and finally just a point. So this cell decomposition of the projective space, very well known. And similarly, this Grassmannian also does have cell decomposition. So it's a union of so-called Schubert cells. Well, isomorphic to some affine space, and indexed by, say, Young diagrams fitting into the k times n minus k box. Well, that's a fact of life, but I will not give definition at this moment, and maybe never at all. But this is true. And then certainly you see that they are not closed subvarieties, they are locally closed subvarieties. They have closures. So this subvariety, well, this cell is a subvariety in the Grassmannian. It's not closed unless the cell is a point. So it's locally closed, and it's numbered by Young diagram lambda. So it's x lambda in the Grassmannian.
What's the power of the
Maybe the total volume of this of lambda. Okay, so this x lambda is isomorphic to A, affine space, and it's locally closed, so we can take closure. And let's see the closure. And it has the fundamental class in cohomology, well, it's even degree cohomology of the Grassmannian. Like this. And so it's in fact they form a basis. So this collection of fundamental classes is a basis in the total cohomology space, ring. And the question of Schubert, or maybe it was in fact one of Hilbert's problems to just compute the structure constants of multiplication in this cohomology ring in this basis. Well, maybe more geometrically, there is the Poincare duality, which identifies cohomology and homology, and then in homology you have to intersect those cycles somehow. They're singular, and that's the problem. Well, maybe the most obvious problem is that they are contained in each other, but then in homology you can shift them arbitrarily, and they will intersect generically transversely, but they are singular, and that's the real problem to compute their intersections. Okay, and the solution scheme is as follows. So first you introduce one very big Grassmannian that contains all the other Grassmannians. It can be baptized something like this. So what can you do? You can, yes? Pardon me? This one? No. This is well, it has no meaning whatsoever. It just the first thing came to my mind. But I will explain what I mean by this. It's not a standard notation by any means. So we have Grassmannian of k-dimensional spaces in like Cn. Pardon me?
We know that these things factorize in even cohomologies, right?
Right? There are no odd. Because of this cell decomposition, there is no odd cohomology whatsoever.
Okay, then in Schubert's problem, shouldn't it still be
Twice? Okay, if you wish. So there is an evident embedding like this. You just add okay, so you can go to infinity, and the union is Grassmannian k infinity. K-dimensional subspaces in infinite dimensional space is the union of the co-limit of this diagram. Okay, now you can also go from Grassmannian of k Cn into Grassmannian of k plus 1 Cn plus 1. Namely, just have a subspace Vk in Cn, and it goes to Vk plus C inside Cn plus. Okay. So you can either increase the second parameter or you can increase both. And the Grassmannian of infinity twice infinity is the colimit of this diagram. Fine. And then we can consider the limiting cohomology, or for Masha I could write twice bullet of Grassmannian infinity, twice infinity with integral coefficients. Now certainly it's another ring, but also a core-ring. And in fact, a Hopf algebra. Since this Grassmannian infinity twice infinity is a Hopf space. And now another vote. Who knows the meaning of Hopf space? Yeah, but again, majority does not know. So let me say that it's something like a group. So there is a multiplication from x times x to x. That is homotopy associative well, at least this. Maybe some more requirements, but at least this. And exactly for having this extra structure, we went to the limit. Well, maybe I'll call it M. So M is the colimit of the direct sum. Just direct sum. Now, since you know about cohomology, you know why it has the ring structure. So multiplication in cohomology is just the factoriality of the diagonal embedding and QNet. So there's the diagonal embedding. And also this by QNet isomorphic to the tensor product. Like this. Okay. And now this multiplication map, M, from x times x to x gives rise to coproduct or co-multiplication from cohomology of x to cohomology of x tensor cohomology of x. Well, we can check that the following key property. It's called bialgebra. Well, let me call it. star maybe. So by algebra property is that M star is a homomorphism of algebras. Right? This is an algebra for the above reasons, and this is just the tensor product of two copies of the same algebra, so it has also algebra structure, and this homomorphism of algebras. So this is some relation between product and coproduct. This is called bialgebra. There's also unit. Well, just from Z to cohomology. And there's also co-unit from cohomology X to Z. Well, there is some extra property. It's called antipode from H of X to H of X. Well, exactly the composition of unit, co-unit, and that antipode is the identity from Z to Z. If it exists, then the whole structure H of X multiplication, well, we just call delta star, co-multiplication, unit, co-unit, and antipode A, this whole structure is called a Hopf algebra. Pardon me? Yeah, because I didn't finish here, but there must be a multiplication that is associative, and also the homotopy inverse. There might be a homotopy inverse. Pardon me? Homotopy, yeah. H space, it's on the one hand homotopy. The etymology is on the one hand from homotopy group, on the other hand for Hopf. Heinz Hopf who introduced this notion. Okay. What I wanted to say that the bottom line is the cohomology of an H space, Hopf space, forms a Hopf algebra. Okay. Now, the usefulness of this notion is in its rigidity, so to say. There are very few Hopf algebras, say, over rational numbers. We discussed integral cohomology of Grassmannian, but certainly we can consider cohomology with rational coefficients, and they will form a Hopf algebra over Q. And there are very few such guys. So there is a theorem, as far as I remember, due to Milner and somebody else, maybe I forgot. Moore, thank you, Kirill. So any Hopf algebra. Another thing is that cohomology certainly is a commutative or maybe supercommutative algebra. But in our case, all the degrees are even, so it's just literally commutative. But any, I should say, supercommutative co-commutative. Hopf algebra over Q is isomorphic to just polynomial algebra or super polynomial algebra. So symmetric algebra in some generators, tensor Grassmann algebra in some other odd generators. So degrees. Maybe I should say any graded. So the degrees of xi are even, and degrees of yi odd. Well, maybe the simplest example is a group like UN, co-complex group, and hopefully everybody knows what this means. Unitary group. You do know. Great. Then it's a group. So for theory, there's a Hopf space. I mean, there is multiplication that is just associative on the nose, not just homotopy associative. And hence, the cohomology of UN with coefficients in Q, well, they cannot have infinite dimensional part because the whole thing is finite dimensional. So it must be purely Grassmann algebra. And so it's Grassmann algebra in the variables, well, y1 and so on, n, I think, yeah. And the degree of yi is 2i minus 1. Okay. Now, it's the cohomology, so it's cohomological degree. But for Grassmann algebra, what matters only is that the degree is odd, so they anti-commute, right? And exterior algebra, so they anti-commute. But it's also z-graded with this grading of generators. Okay, so now back to our initial Grassmannian problem. Here, for Grassmannian, all the degrees are even. So it's purely symmetric algebra. Cohomology of Grassmannian infinity twice infinity is the symmetric algebra of well, x1 and so on. But in fact, because it is very big, like, for example, if we considered cohomology of just P infinity, project space, but infinite dimension, the union of all finite project spaces, this will be Z of just one generator, and degree of this generator would be 2. Yeah? And here you will have x1, x2, or maybe I should say c1, c2, c3, and so on. And the degree of ci will be 2i, and the standard name is the Chern class. Ci. Meaning that this space is actually the classifying space for complex vector bundles, and any space with a complex vector bundle is equipped with the classifying homotopy map, well, classifying map to this Grassmannian, well-defined up to homotopy. And if you pull back those canonical generators, they will give you the Chern classes of the initial, original vector bundle. Okay.
Sorry,
yes.
does this Milnor-Morse theorem say something about coalgena structure?
Oh yes, it does. Well, so I call it M star. Yeah, M star over xi is 1 tensor xi plus xi tensor 1, and the same for y's. Okay. So if you still remember what we started with, this Schubert problem, then its solution just says who are the Schubert classes in terms of these generators. Yeah, I just erased the Schubert problem. Sorry for this. Still the solution of Schubert problem. Is explicit formula for fundamental classes. X lambda bar in terms of generators Ci. Yeah, we certainly do know how to multiply polynomials in infinitely many variables. What we must find out is how to write down those Schubert bases in terms of multiplicative generators. So this thing, the symmetric algebra over C1 and so on, over Z, well, it has a special name. It's called lambda. This lambda is the ring of symmetric functions. Now there is some maybe clash of notations. I apologize for this. Symmetric functions in variables x1, x2, and so on. And this is the standard notation, so I cannot change it. Lambda is the ring of symmetric functions in variables x1 and x2. I understand, and so what?
Okay.
Yeah. Now, for example, there is a symmetric function like this: x1 plus x2 plus x3 plus so on. And it's an infinite sum, but why not? Again, and it's called E1. There is also x1, x2 plus x1, x3 plus x2, x3 plus and so on. You understand what I mean? and it's called E2, and so on. So see, these are elementary symmetric polynomials. Yeah, certainly we also have x1, x2, x3, x4, but we have to symmetrize it. So we have to plus x1, x2, x7, x199, plus so on. Yeah, no, infinite product, no, that's not allowed. Infinite sums are allowed, but not infinite products. So next time I will give a formal definition, and it will be a tedious and boring class. But today let me just continue. So it's called E4. So now CI is actually EI. Those Chern classes are just elementary symmetric functions. And then if we identify it like this way, then the class of Schubert variety x lambda will be a S lambda Schubert function. Schur function, sorry. So this is the solution. Well, then maybe the problem is how to multiply Schur functions, but well, there's a well-developed techniques for this. The coefficients are called Littlewood-Richardson coefficients. The structure constants. In basis. And are called the Littlewood-Richardson coefficients. C nu lambda mu. Okay. Maybe let me add a few words about the Hopf algebra structure. In terms of lambda. So the key point is that this lambda is a universal example, and very many problems in various parts of mathematics, they all reduce to the study of this one universal ring lambda. I just started from some topological problem, but many problems in representation theory and special functions and what not, integrable systems, they all reduce to the study of the same ring lambda. So lambda is a Hopf algebra. Say what I the coproduct m star f of x, it certainly lies in lambda tensor lambda. And this lambda tensor lambda can be viewed as functions in x variables and y variables. Okay, and in this sense, this coproduct is just the same function, but considered as a function of x and y, by definition. Yeah, by definition. for example, m star over En will be 1 tensor En plus E1 tensor En minus 1 plus so on plus En minus 1 tensor En E1 plus En tensor 1. Pardon me? Вокруг плюсиков, кружочки лишние, да? Плюс, плюс, плюс. Thank you. Oh, and one. Thank you. So you may view this as a definition, or that as a definition, whatever you wish. Well, there is a scalar product. On lambda, in fact, it's lambda is graded, and it's on each particular graded part separately. So what does it do, this scalar product? Well, for example, the scalar product of the Schur basis is just delta lambda mu. So the Schur basis is orthonormal. There are many other equivalent definitions, and we'll study them starting next time. But what I want to say is that m star and m, just usual multiplication, are well, how to say it, adjoint, dual to each other. With respect to this scalar product. Well, there is some involution omega that takes ER to the complete symmetric function or homogeneous symmetric function and back. And this antipode A on the degree n part, A is equal to minus 1 to n times omega. So, omega is an automorphism, and antipode is also an automorphism. They are almost equal up to this minor sign. Well, I explained that lambda really is a Hopf algebra, and moreover, the structure of Hopf algebra is self-dual with respect to this nature of scalar product. Okay. Now, the next appearance of this lambda in representation theory happens for representations of symmetric groups. And if anybody went to Alchansky course last semester, then he knows this. So another appearance of lambda is just the direct sum over all n of should I say K group? I don't know. Is it okay? K group of representations of a symmetric group number n. Is it clear what I mean by this? No? Pardon me?
No, modulus and where
So, well, it's for each particular, for any group G, representations, I mean over complex numbers, or maybe I should say complex group rings of symmetric groups. I mean, if I have another field of positive characteristic, then it changes. Pardon me? This is a symmetric group. On n letters. Yeah, but still. So for any group G, the K group of representations of G, several complex numbers, has a basis of isomorphism classes of irreducible representations of G. Yeah, and it is absolutely right. So it's isomorphic just via character map to the space of class functions. So functions on G invariant with respect to the adjoint action of G. So I could write here the class functions on the symmetric groups. Okay, and then I have this thing. So, well, this grading in the right-hand side corresponds to the usual grading by degree in the left-hand side. And what about, say, coproduct? In the right-hand side. Well, we take a representation, or maybe, pardon me? For symmetric functions, in this presentation, only infinite sums, certainly, because they are in infinitely many variables. X1, no, doesn't work. You have X1, just by this symmetry, you must have also X2, X3, and so on. If you have X1, X2, you must have all the things like this. In degree 1, you have just this, nothing else. In degree 1, it's one-dimensional. In degree 2, it's two-dimensional. You have elements like this, and also X1 squared plus X2 squared plus X3 squared, and so on. But we will do this very slowly and formally next time. And today is just a flight of free thought. The coproduct in the right side is just a restriction. From Sn to Sk times Sl, well, direct sum over all K plus L equals N. Yeah, so you have certainly an embedding from this product to that. These are permutations that preserve the first K letters. These are permutations that preserve the last L letters. And you have such a subgroup, and you can restrict. And this gives you a map from Kn to K tensor KL. And you take direct sum over all decompositions. Now the product, it's just a joint, so it's induction from K times SL to Sn. And again, another vote. Who knows what is induction for representations of finite groups? Well, about half, but fine. That's what I mean. Fine, and then there is a theorem, maybe essentially due for Frobenius. And this was the start of the representation theory at the turn of 19th century. That indeed, with these operations, we have an isomorphism. Okay, and again, the basis of irreducibles corresponds to sure functions as lambda. And this allows to compute explicitly the characters irreducible characters of symmetric groups. Okay. Well, now, from this we have another more or less tautological interpretation of lambda. So we had already two interpretations of lambda as cohomology of infinite Grassmannian and as representation rings of symmetric groups. But these were highly tautological. And the next interpretation is tautological. So lambda is the representation ring, or as Masha says, class functions. Of GL, but since it's infinitely many variables, then we should have also infinitely many variables here. But the meaning of this infinity is, again, something non-standard, maybe. But maybe I should say GL and C for n very big. Okay, and why this is so? So again, have you heard about the sure while duality? No, so this is by well, maybe I should say it this way. So first of all, the class functions on GL and C. So these are functions on GL and C, invariant under GL and C conjugation action. And then we can restrict them to some diagonal torus, and the conjugation action on the diagonal torus just permutes its coordinates. and there's just a restriction map, which is an isomorphism, and it is an isomorphism by Chevalier theorem to the functions on this diagonal torus. Invariant under permutations of its coordinates. And these are just symmetric functions. In capital N variables. Just diagonal entries of this torus. So just it's tautologically lambda. That's what I mean. As for sure Weil duality, well, we can consider this bigger GLN. It acts on Cn. Okay, so it will also act on Cn tensor power small n. Okay, but here you will still have the action of GLN, but you will acquire another action of a symmetric group on small n variables. Just by permutation of tensor factors. Okay, and the key statement is that well, those two actions certainly commute, but they are centralizers of each other. So everything that commutes with GLN lies in the group ring of Sn, and everything with which commutes with Sn lies in the so to say group ring of GLN. So these are commutants of each other, which means that given an irreducible representation of Sn, the isotypic, well, maybe let me denote it some way. L lambda. Because, well, we've heard already that the irreducible representations of Sn are indexed by Young diagrams. The isotypic component, the well, L lambda isotypic component of Cn tensor n is an irreducible representation of GLN, and its character, that is a restriction of its corresponding class function, trace function, to the diagonal, is just the same Schur function as lambda I've had here. It is well, it's a tautology, but a tautology within the framework of representation theory. So if you are not yet well acquainted with this, it does not look like a tautology, but we'll go over it slowly afterwards. Okay, so this was a tautological interpretation of lambda. And maybe let me say some more concluding words. there is a similar story to this collection of representations of various symmetric groups. And well, maybe you've heard that in some sense Sn is the q equals 1 limit over GLN over a finite field Fq. So in many respects, symmetric group Sn behaves like the group GLN over a field of one element, so to say. And again, we can play the same story as we did here. We can consider the direct sum over all n, the k groups of representations of GLN Fq. But now this will be much bigger, and still it will be for the same reasons. We can consider restrictions and inductions, and it will be commutative, co-commutative. So it will be again some Hopf algebra, and by Milnor-Moore theorem, it will be polynomials in many variables. So it will be just a tensor product of many copies of lambda. But we can distinguish one main copy of lambda inside here. So maybe tensor product of many copies of lambda, and one copy of lambda is the direct sum over n of k groups of representations of GLN Fq, which are called unipotent. And the unipotent means, in this GLN case, that they have, well, say irreducible representation is called unipotent if it has non-trivial invariance with respect to upper triangular subgroup. So generated by its invariance with respect to the upper triangular subgroup. Okay, so for each n, there are not too many such representations. They're numbered by Young diagrams, partitions of n. So in particular, it's independent of q. And the restriction of such unipotent will be again unipotent, and induction of such unipotent will be again unipotent. So they really do a sub Hopf algebra isomorphic to lambda. Okay, but on the one hand, there is some q here. On the other hand, we obtained an isomorphism with something which does not depend on q whatsoever at all. And this is strange. And maybe a reformulation of this is the so-called whole algebra of the formal power series over FQ. So just finite dimensional representations of this. But finite dimensional representations of this are vector spaces with action of this generator T. But since the action of T extends to the action of formal power series, it can only happen if the corresponding linear operator is nilpotent. Otherwise, it makes no sense to take infinite sums. So this whole algebra has a basis of isomorphism classes of vector spaces over FQ equipped with a nilpotent operator. Well, and the multiplication well, we have say V1, and I want to multiply it with V2, and it will be the sum of some structure constants. I don't know how to say, C, V1, V2, V3, the class of V3. So this structure constant, CV1, V2, V3, is the number of all subspaces in V3 isomorphic to V1 such that the quotient is isomorphic to V2. Since everything is over finite field, everything is clearly finite here. Well, we have to check that this given structure of associative and even commutative algebra, and this would be isomorphic to lambda. Yes, certainly. Finite dimensional spaces, yes. Yeah, very good with T, yes. V1 T, V2 T, and V3 T. So these exact sequences I mentioned, they must be compatible with the action of T. Everything is compatible with the action of T. And now note that the basis, well, a natural basis, is indexed by partitions, just by the Jordan normal form. Yeah. So we have. Pardon me.
Partitions of what?
Of everything. If you want an n-dimensional vector space V1, then all the isomorphism classes of nilpotent operators by Jordan normal form are now indexed by partitions of n, of dimension of this. Well, there is some contradiction. I think it's actually 2 minutes before the end of the lecture, right? But this watch is more optimistic. This clock is more optimistic. Yes. It's just the same thing. I mean, this whole product corresponds to an induction. So it's just a reformulation of what I said before. This whole algebra is another way to speak about unipotent representations of GLM. So, have this natural basis u lambda is this basis. So corresponds to the isoclass of Jordan type lambda. And then the question is, if we identify this whole algebra with lambda, which way? Well, for example, we can take Vn. This is the class of Fq to the n, and just zero operator. Why not? And let it go to Q, maybe negative n, choose 2, En. Why not? This will be our isomorphism. Then the question is, where do these guys go to? Then u lambda will go to the so-called whole Littlewood polynomial p lambda in lambda, but now tensor polynomials in Q, or maybe to be on the safe side, would rather invert Q. Yes. Maybe I should also. Yes. Well, that doesn't really matter. Just it's so-called excision of precision. We'll go over this slowly in a couple of months, but today it's just summary renormalization. So they go to the whole Littlewood polynomials. So they're polynomials in symmetric polynomials in X's and also in one extra variable Q. And well, it's possible to compute them explicitly. For example, it's known that P lambda at Q equals 0 is S lambda, and P lambda at Q equals 1 is M lambda. So they interpolate between those two. And they can also be, well, there is an explicit formula for them, but they can also be characterized by the property that P lambda, they're M lambda plus some smaller junk, and they form an orthonormal base with respect to this scalar product I mentioned in the very beginning, but deformed. Deformed with respect to Q somehow. Those whole Littlewood polynomials, they can be, they have many equivalent, many various equivalent definitions. One of them is just application of a Gram-Schmidt orthogonalization process to the monomial basis M lambda. Okay, and well, I have to stop, but maybe in the most reckless fantasies of mine, we can even go further in this course and consider McDonald polynomials. Which are some deformations of whole Littlewood polynomials depending on one extra variable t. Okay, so that's something about I plan to do starting next time. But next time we'll start from scratch. So you shouldn't have understood anything today. You were not supposed to understand anything today. And where is my list? There. Everybody inscribed? Okay, thank you.
Домашние задания каждую неделю будут?
Yes, I will send them out weekly.
Дедлайны тоже не слишком жесткие.
Just in a week. The deadline is in a week. Every Tuesday.
Можно вопрос по поводу возможного переноса? Нет, то есть у нас пересекается с другим курсом во вторник. Просто с миссом Аршанского
О,
пересекается.
вот, это ужасно, да.
Вот.
А что делать? А когда он? Прям
Ну,
буквально в
буквально
4?
час.
Что же делать?
Ну, можно на пару раньше, если у вас получается.
Я, пожалуйста, я могу, но... А как...
Ну, в другом кабинете можно.
Нет, мне это наплевать, пожалуйста, а все остальные как?
Ну, да, я понимаю, это надо обсудить как-то, но я просто хотя бы у вас хотел сначала спросить.
Я
если у вас
готов,
тоже
пожалуйста, с удовольствием. То есть я тогда могу написать вот всем по этим адресам, готовы ли они перенести.
Да, нет, ну мы группу создадим в Телеграме, там как-то решим сами. То есть
хорошо.
потом напишем вам.
Тогда мне надо вообще ничего не делать. Я просто готов во вторник в любое время, да. Но ничего делать не буду до получения ваших указаний. Хорошо. Ой. До свидания. Да. Ага.
Почему бесполезно брать сюда, если на то, что мы не работаем, почему бесполезно брать еще бесконечно энергию? Это этот самый